Here we have a file, 7 megabytes. You need to know what these units mean. And although we haven't discussed that, we'll refer to some of the handouts. Here, M is mega. And in our course, we're going to assume that we use the decimal prefixes. That is, K, meaning kilo, kilobytes, for example, corresponds to 1,000. That's the area for discussion, and we'll come to that. So in this course, what we're going to do is say there's two answers here. K, kilo, can be in the decimal form, where it means 1,000, or in the binary form, where it means 2 to the power of 10, which is slightly different from 1,000. It's 1,024. And both are used in practice, and in different fields they're used. Mostly when we talk about files, you're right that we use the binary form, 1,024. Okay? So if you see M, it's not 1 million, but usually represents 2 to the power of 20, which is slightly more than 1 million. I can't remember the exact number. So there are binary prefixes where, for example, K equals 1,024. Usually used in files, but when we look at download speeds, for example, we usually use the decimal prefixes like 1,000. It's confusing. To avoid that confusion in this course only, we're going to always use in the examples and in the questions the decimal prefixes. Okay? Doesn't matter if you answered that wrong in this quiz because you used the binary prefix, that's fine. But just to avoid confusion in this course, in all the examples I give and all the questions, unless we state it, if you see K, it means 1,000, not 1,024. Whether it's size of file, download speed, something else, it means 1,000. M means 1 million, uppercase M. G, giga, is 1 billion, 10 to the power of 9. Why do we do that? Well, it makes my calculations much simpler, especially when I go through examples on the board. I can divide and so on much easier when I use decimal values as opposed to the binary values. It's not true in real life. In real life, sometimes you'll see an M and it may mean 1,024. Sometimes it will mean, you'll see a K, it will mean 1,024. Other times it will mean 1,000. There's a small difference. That's something you need to deal with. In this course, to keep things simple, we're going to always use 1,000, 1 million, 1 billion, and so on. Okay, that's the first assumption for this course. What's B mean? In this course, we're going to assume uppercase B means bytes. Okay? Lowercase b means bits. Okay? And there are how many bits in a byte? 8 bits in a byte. Okay? Lowercase b, 1 bit. Uppercase B, 8 bits or 1 byte. And that's normal in practice today. In the old times, 1 byte wasn't necessarily 8 bits. You could have a 7-bit byte. That added more confusion. But most times now, when you see a byte, it means 8 bits. And that's what we assume in this course. So uppercase B, bytes. Uppercase M, mega or 1 million. Therefore, 7 megabytes is the same as 7 million bytes, which is the same as, if we multiply by 8, 56 million bits, lowercase b. So in this case, if we have a file of 7 megabytes, we want to download it, 56 million bits. The speed at which we transfer those bits across our network or our link is 100 kilobits per second, where K here is 1,000. So at a rate of 100,000 bits per second, at some rate of 100 kilobits per second, or 100,000 bits per second, how many seconds does it take? Then we have this number of bits transferred at this speed, and we just divide those numbers, and what do we get? 560. This 56 million divided by 100,000 is 560. And the units, here we have bits, B, and we're dividing by bits per second. Which is the same as bits times by seconds over S over B. The B's cancel out. The units are seconds. Make sure you give the right units in your answers and the right prefixes, or a correct prefix. Bits divided by bits per second gives us seconds. So that's the main point of this question, is to make it clear of the assumptions that we're going to use about the decimal prefixes, the bytes and bits, and some of the other units that we'll use throughout the course. The mathematics is easy. Any questions about that? Of course, some of you had different numbers, but the same style of question. The units and prefixes are summarised in one of the handouts that you have. Definitions and concepts. It's in your handout somewhere. It's on the website as well. There's some acronyms that are commonly used. And then something about units and prefixes. Common ones that we will see, not all, may not use all of them: seconds, meters, bits, hertz for frequency, radians or degrees for angles, watts, decibels. And then the prefixes that we'll use, or some of them we'll use, going up: K or kilo, 10 to the power of 3, M, mega, 10 to the power of 6, 1 million, G, 10 to the power of 9, tera, 10 to the power of 12. And going down, milli, 10 to the power of -3, micro, nano, and pico. We'll use some of those, or you'll see some of those during the course. You need to, if you don't know them off the top of your head, you need to know them, not just for this course, but for all your studies and professional life. So that's one example quiz question. What other? Some students already realised that the way that Moodle is set up, there's, when you need to give a short answer, like a word or a phrase, what it involves is me programming in the correct answers. And sometimes I cannot think of what you're going to think of. So I may not include all the correct answers. I'll try and fix them if I do miss them. But for example, one of the questions was, what protocol is used for web browsing? Hypertext Transfer Protocol, or HTTP, was a short answer. The correct answer according to the system was either the full Hypertext Transfer Protocol, spelled correctly. If you misspelt it, the system would mark you wrong. Okay? It's not smart enough to detect the spelling mistakes. Or the abbreviation HTTP would be marked correct. One thing I didn't mark correct, and it was something I missed, is the full spelling followed by in brackets HTTP, which is also correct. So in some cases we will need to iterate and improve upon some of the questions, but just be I think you'll know when you see the answer whether yours is correct or not. Okay? Let me know if you see an answer that you think is wrong or not appropriate, and we'll fix that. What else can we say about the quiz? Any questions about the quiz or any problems with the quiz? For those who have arrived late, 77 of the 80 odd students have attempted, so I think most of you here have completed the quiz. That's good. Today we're going to talk about protocols. What is a protocol? Any of these students here? Stand up if you're on one of those lists. Don't be shy, there's no problems. Stand up, just I'd like to meet some of the students, know who you are. Okay, some of them are IT, some are CS, that's okay. All right, that's fine. Okay, you can sit down. We may take one of you as a volunteer in a moment. Make sure you do the quiz on your own, remember? Okay, don't sit in a group in the Macintosh lab or in one of the labs and all answer the questions at the same time. Try to do it on your own. We may call upon some volunteers shortly. Today we need to tell you what a protocol is, and more importantly, what a protocol architecture is. When I've been in Thailand for about 6 years, 5 to 6 years, one thing I still don't understand, or I do not fully know the procedure, is when you greet someone, what do you do? When you meet someone in Thailand, what do you do? Okay. Why, I can't even pronounce it. Why, okay, why. How does it work?
Grasp your hands together.
Grasp your hands together.
And you bow your head.
When do you do that? When you make contact with someone, okay. Are there any rules? If I'm new to this country, or I've been here for a while, but someone's new to this country, you need to describe them. When do you why to someone? What do you tell them? Every time? Every time I meet you, do I have to? And do I have to do it first, or do you do it first? Okay, there's something about the seniority of the person. Maybe the younger person should do it first, and then the older person should reply. Let's write a set of rules so I can remember, okay? And then we'll look at them and analyse them a bit. I'm going to write down the rules that you tell me. So you said something about when I meet someone, or when we greet someone. So from my perspective, let's say I'm walking around. Let's say we're at the start of a state. I want to start this procedure for how to greet someone in Thailand. So there are different cases, is that right? That is, if there's someone younger, you do something different if there's someone older than you, okay? So let's write down those cases so we can remember. So if I meet someone who is older than me, that is, if some senior person arrives, I'm here and some senior person walks into the room, someone older than me, what do I do? Okay. The action I take, if a senior person walks in, I need to why to them. Okay, that's the basic rule. And then what do I do? Should they why back? Yes, so I may wait for them to respond. Okay, so after I take that action, I may wait for some response. Okay, and depending upon the response, I may take different actions. What if a junior person, someone younger than me, comes into the room? What do? I wait for a response first. I do not initiate the greeting. Okay, let's leave it there. It's either senior or junior. All right? It's not like that. Sometimes, how do I know how old they are? Or relative to me? That's even harder. All right? So I'm waiting for a response. So I've either done one of those cases, and now I'm waiting for a response. And, okay, if I receive a response, if I receive the response from the senior person, what do? If I've received a response, it means I've already wired to them, so they have responded back. Now we've greeted each other. We do what we want to do. We start talking, whatever we intend to do. Let's say we start talking and we're done in terms of the greeting part of it. Now we can start our conversation. Okay, that was easy. If I receive from a junior person, what do? I wire back. I respond. That is, they greeted me and I respond to them. And then start talking. I think after I respond, I think we're done. Okay, easy. What if, okay, a couple of other cases, I wire to a senior person and I'm waiting for the response. What if, or maybe what if I wait too long? What do? If they don't respond to me? Come on, tell me what to do. Do I just stand there? Leave? Maybe if they're a senior person, maybe I'll forgive them or just start talking anyway. Okay, depends on the situation, of course. Maybe, okay, they're not going to respond to me. I wait for 5 seconds, 10 seconds, and then start talking because it's okay. But maybe I'm a little bit nervous because they didn't respond to me, okay? All right, what if I'm waiting for a response from a junior person, someone younger, but I don't get a response? What do? Ignore? Okay. Walk away. Okay, ignore them. All right. Some rules for how we greet people. There are some other conditions, of course. Like we said, what if we cannot determine the seniority of the person, who wires first? So it can be more complex than this. But this is a protocol for how humans greet each other. Okay? And we've described that protocol with a set of rules. And I've written it down such that we have really two states that I'm in. The first state, the start state, or maybe I'd call it the idle state. When I start this protocol, I'm idle or I'm in the start state, and there are different events that can happen. Either a senior person arrives, that's an event, they walk into the room, or a junior person arrives. So the event has different conditions. Person arrives, person is senior, or person is junior. Depending upon those events, I take some actions. In this case, I take an action, I wire, and then I move into some other state. I wait for a response. So we have some states that we're in, some events that happen, and some actions that happen, and moving to other states. Here we've described the second state. I'm waiting for a response. Different events may happen. Either I receive a response, or I have a timer running. I have my stopwatch running and I wait for 5 seconds. If I don't receive a response within 5 seconds, then I take some other action. Okay? So we have events which are In this case, people arriving or timeouts occurring. I'm waiting for too long. That is, my stopwatch reaches some value and I say, okay, I give up, I'm going to walk away now. And different actions that we may take. This is about humans communicating. We need to do the same thing but for computers communicating. My computer wants to talk to this computer. They need to greet each other or to make some negotiation to get started in their communications. How do they do that? That's what protocols describe. And we can simplify protocols in terms of really these if-else statements. If some event happens, take some actions. So we're going to spend a lot of this semester talking about protocols, but remember they are as simple as this, or this is an example of a simple protocol. The problem with computers is that computers do what they're programmed to do. Humans, all right, we compute things, but we can use our brain to work out how to respond. If you need to write down the exact rules, you need to be more precise and say, all right, I say, if wait too long, how long? How long should I wait for a response? Some people may say 1 second, some may 5 seconds, maybe 10 seconds. For a computer, we need to tell it exactly. You must wait for 5 seconds before you take this action. So it needs to be precise with computers. So protocols, we need to specify exactly how the computers should operate. Otherwise, the computers, when they're communicating, may get into a state that they don't work. One state in this protocol, what if someone arrives and I don't know their seniority or I don't know their age compared to me and they don't know my age compared to me? What do they do? Well, we don't have a case for that. I don't know whether if they're senior or junior, but we need another statement. If I don't know their age, maybe take some actions. So we need to be more precise when we talk about computers, otherwise things will go wrong. So that's a protocol. A very simple one. We need to talk about how we design and structure protocols for the internet and data communications. What is a protocol? A set of rules that 2 or more peer entities obey in order to communicate. In our example, the peer entities were the 2 people, okay? But in general, we just refer to this some entities. Normally, we talk about 2, 1 to 1. But in general, we can have more than 2 involved in a protocol. We can have multiple entities. Most examples we'll see there are just 2 entities. So we have a set of rules. In the previous example, they were described by a set of if statements. All right, going back to our example, are there different types of whys? What do I do? You said I put my hands up, and where do I put them? Do I put them here? Do I put them here? Here? Are there different positions I could put them? It depends on who you're greeting, I think. If it's informal, someone you know, maybe you may not, or may not have them so high. Maybe it's someone you highly respect, then they may be slightly higher. Is that right? So there are different formats of the message we're sending to the other person, depending upon the situation. So in the same with computer protocols, the message that we send between the 2 entities has some format or some syntax. We need to describe what that is. In our case, can we describe it? So I have a record. Maybe there's different ways. So what do I do? Maybe hold or hands together, raise to above head, and then I bow as well. So That may be one type of wire. I hold them up high and I bow. But another one may be a less formal. And so that's a different type of message. It has a different type of meaning. Any more? I see some from students. When they've got a handful or something, they've got it very quick. Okay, so there are different types of messages we can send to the other person. We need to describe them because they have different meanings. And same when we talk about computer protocols, give the syntax of the data or the messages that we need to send between the entities on those computers. So we have a set of messages and a set of procedures that, or a set of rules that each peer must follow, including things like timing information. How long do I wait? You must wait for exactly 3.6 milliseconds before you respond. So we need to be precise. So that's a protocol. The problem in data communications is that we cannot have one protocol that does everything. Because communications is very complex, there's many different things that we need to do. We mentioned some of them last week. There are many different things. What we do is apply the divide and conquer principle. Instead of having one protocol that achieves all our goals, we have a complex problem, communicate between two computers. Many things to do. So we divide that into many smaller problems and produce protocols that solve the individual small problems. Divide and conquer. In data communications, the way that we, or the notation and terminology we use to talk about how we divide the problem into different tasks is we look at it from a perspective of layers or a stack. We break communication tasks into subtasks. So the overall task, communicate between two computers. Break it into many subtasks. And we implement the different subtasks in different layers. And we'll see a diagram in a moment, where the layers are arranged in some stack, one on top of the other. Okay? And we'll see that, or these small notes here, a layer in the middle makes use of the functionality of the layer below it and provides a service to the subtasks in the layer above it. If we combine our layers together, we get what's called a protocol architecture. And it's best described with some examples. I'll go forward and then come back and describe this in a bit more detail. But here's an example of a protocol architecture, or a stack. We just draw a diagram where we separate into, in this example, 3 different layers. Why do we do that? We'll implement, or we'll achieve different tasks related to applications in the top layer, and different tasks related to how do we access a communications network, how do we use a communications network in the bottom layer, and we need to describe a bit later, but how do we transport data between computers in the middle layer. That is, in this simple example, we've said to communicate between computers, there are many different tasks. Let's group them into 3 different layers and call them application, transport, and network. This is our protocol architecture or protocol stack. It's divided into 3 layers where there would be protocols in each of these layers. There may be some protocol for how does this computer connect to a device in the network. How does it send electrical signals across the wire? There may be a protocol in the application layer for how does your web browser create a message to send to a web server, a protocol like HTTP. So we have a protocol architecture which is made up of multiple layers. Within each layer may be multiple protocols, and they achieve different tasks, or they perform different tasks. In this course, we're going to focus on just one protocol architecture, the TCP/IP or the Internet Protocol architecture, but there are others. Why do we break it into layers? Because we can't do everything in one protocol. It makes sense. In the same way, when you write a piece of software, you don't put all your code in the main function or the main class. You break it into sub-functions or into classes. That's the same concept here. We don't put all of our data communications functionality into one protocol or one piece of software. We break it into subtasks and separate it. In this example, and this is just a simplified example of a protocol architecture, let's view our computer network with laptops and PCs, some cables all connected together, as from the perspective of we have applications. Applications run on our computers. That's what the user wants to use. The user may want to access a web server, that is web browsing application, may want to download a file, FTP or file transfer, send an email, instant messaging, and so on. So we have applications that the users use. We have our computers, so the devices on the network, and we have the network, which is mainly the cables. We'll show some cables that connect the computers together, possibly to other devices like switches and routers. In this example, let's divide the tasks for communications into 3 different groups, or 3 different layers. We'll say we'll have some protocols that support applications. For example, I'll have a protocol that supports web browsing. I'll create a different protocol that supports email, and another protocol that supports instant messaging, and so on. Each of those protocols we'd classify or group into the application layer. They are protocols that are built to support specific applications, and we group them all together. Let's call it the application layer. Many applications want to do the same thing, send some data reliably across the network. When you're sending an email, you're sending some data across a network. When you're downloading a web page from a web server, you're receiving some data, that is, the web server is sending data to you. When you're sending an instant message to your friend, it's just some data being sent across the network. In all cases, we want reliability. Last week we mentioned accuracy of our data. If I send something, it needs to be the same at the receiver from what was sent. It needs to be accurate. Sometimes, or rather than implementing reliability mechanisms in individual protocols for each application, it's common to create one protocol that provides reliability for many applications. My web browser needs to be able to reliably send data. My email client needs to be able to reliably send data. So does my instant messaging application. Rather than having to have the functionality for providing reliability in individual applications, in this case we're going to separate that out and put it into its own layer. Let's call it the transport layer. It's responsible for transporting data across the network, usually in a reliable manner. So we may have one protocol here, and the 3 protocols or the multiple protocols in the application layer may use that one protocol. Rather than implementing the functionality in the individual applications, we implement it just once, and the applications make use of that. Then let's say we have one other layer for accessing the network. I have my computer, which has some LAN card in the back, okay, either on board the motherboard or a separate device. Okay, you've seen the little slots there, I'll pass them around. And we plug a cable into the back of the computer, and then we need to be able to send data across this cable to the other device at the other endpoint. So the protocols to achieve the interface specification, to be able to send signals across this cable, let's say a part of the network access layer. How do we get data onto the network, or how do we access the network from our computer? Like the very low level things, how do we generate signals to send from this piece of hardware is one example. So we divide tasks into different groups, consider them as layers. In this example, we're going to have 3 layers. One to do with applications, what the user uses. One to do with getting data across the network in a reliable manner. And the other of how to get signals out onto the link, network access. So in our example network, if we have 3 computers, we have applications running on each of those computers. Web browsers, file transfer applications, instant messaging, whatever applications we want. Those computers are connected, in this case, to a network via some cable. There's a cable plugged into this computer, and it connects into the network. In this example, we don't show the devices in the network. It may be just one device, a switch, for example. An old switch where we have some 8 sockets in the back. We take our 3 computers, each with a cable, plug into the switch, and effectively all 3 computers are connected into the one network. So this cloud may be a single switch, or it may be as complex as the internet, covering the globe. When computer A wants to talk to computer C, that is, the user on computer A starts their web browser, an application. They want to contact the web server running on computer C. The web server is another application. Then their web browser will need to send some data to the web server from the application here, a piece of software, to the application, the web server on computer C. The way that we consider layers is that our user starts the web browser, enters in some URL, some address, clicks on go or presses enter, and that forces the web browser to create some data to be sent to computer C. This one maybe captures it a bit better, although it's computer A and computer B. At the top, our application generates some data, this grey box at the top. The application protocol, which is specific to the web browser, creates that data and needs to send it to computer B. They don't send it directly, they send it to the lower layer. That is, the application layer protocol at this top layer sends the data to the software at the next lower layer, in this case the transport layer. There's a protocol in the transport layer that's going to reliably deliver our data across the network. So here's where we separate out the functionality. The application layer protocol just does things related to web browsing. Once it's prepared the data, it sends it to the piece of software that implements the transport layer protocol. The role of the transport layer protocol is to make sure that data, whether it's a web page, an email, an instant message, make sure the data is reliably delivered to the other side, to the destination. When I say reliably delivered, I mean accurate. If the data is a message saying, "I love you," then what the other side must receive is the exact same text, the exact same data. If there's some error in the network, it's the role of the transport layer to fix that error. One way to fix errors is to send again. If you send and you recognise there's an error at the receiver, send again. If there's no error at the receiver, then we're successful. If there's another error, resend. Keep resending until the receiver receives an exact copy of what was sent. That part of resending is part of the transport protocol in this example. The application doesn't have to do that. The transport protocol does it on our behalf. When the transport protocol processes the data, what it may do is add some addresses to indicate where we're sending this data to. On this slide, the example is that we have two applications on computer A, identified just by numbers. Application 1, application 2, 1 and 2. And there are two applications on computer B, 1 and 2. For example, the web browser or server and an instant messaging application. The web browser wants to send the data to the web server, not to the instant messaging application. Okay? We want to send to the application of the same type. How do we do that? With the data that we want to send, we can include an address of the application. And that's shown in this example. Okay, computer A is sending data from application 1, and it should go to application 2. We'll see when it arrives how that's dealt with. We include that information with the data. The transport layer sends the data, as well as those two addresses, the from address and the to address, to the lower layer, the network access layer. The network access, for example, is going to create some electrical signal that carries bits across this cable. And the protocol implements how that's done. Another thing that the network access layer does in this example is includes the address of the computers in that message. Addresses 1 and 2 were the addresses of the applications. I want my web data to go to the web application at the computer B. But we also include the address of the computer that we want to reach. I want all of this data to go to computer B. And it's coming from computer A. So include the addresses with that message. Somehow transmit all of that message across the network. How is that transmitted? We will spend several topics on the way to transmit bits as signals. Magically, it's transmitted across the network and it arrives at computer B. Why did it arrive at computer B instead of computer C? Because of the address. The network sees, okay, here's a message to computer B. There's a computer C here. The network realizes it must deliver this message to computer B, not to C. This is our measure of, what do we say? Delivery. Last week we mentioned delivery, accuracy, and timeliness. We need to deliver the data to the right destination. And we use addresses to do that. The network access layer receives this message. It realizes this is to me. Because it knows I am computer B, the message is to computer B, therefore this is to me. It knows that the message is delivered to itself. Processes the message and sends up to the next layer, the transport layer, what was inside the message, and that's the grey part here. We remove the information about the to and from address from computer A to computer B and send the rest to the transport layer to deal with it. The network access layer is finished. Its process or its job was to receive the bits, check if it was to me, if so, remove those addresses and send the rest to the transport layer, and then let the transport layer do its job. The transport layer checks if the data is received correctly. There are no errors in it. And we have a topic on error detection and correction. There are algorithms to check that there is no errors in the data. You have probably heard of CRC checksums. That's an algorithm to check that the data received doesn't have any errors in it. Parity checks is another way. We'll cover them later. Transport layer receives the message from the lower layer, looks at the addresses. Okay, it's from application 1, it's going to application 2, remove these addresses and take just the data and send that to application 2. Not to application 1, send it to application 2, the web server, for example. The web server receives the data and does whatever it needs to do with that data. If it's a web server, it probably looks at the data, and then the web server may respond with a web page to the web browser. But we don't show that in this process. What we're trying to illustrate is the relationship between layers. And also a new thing that we've introduced here is that we have our original data that we want to send from one application to another, but we attach other information to that data. In this example, we attach some addresses. The entire message that we send we'll often refer to as a packet. We send a packet across the network, where that packet contains the data plus some extra information, usually referred to as headers. So, and the next slide will describe that. Going back, we have protocols which are rules for entities to communicate with. In data communications, instead of having one large complex protocol, we divide the tasks for communications into many different protocols. And we group those protocols into layers, where the layers together become a protocol architecture. Here's an example protocol architecture where we have 3 layers. We'll see a real one shortly. The layers are implemented in in each computer. That is, in this example, all 3 computers implement those layers. Whether it's software or hardware, it's implemented somewhere in the computer. And we communicate between computers by creating some data and passing it down through the layers inside that computer, across the network to the destination computer, which then processes what they receive and send it up to the eventual destination application. And then they do what they need to do, depending upon the application. So that's what we know so far about protocols and protocol architectures. This picture, these boxes here sent across the network, we have data from application 1 to application 2, from computer A to computer B. All of that we may call a packet, or maybe more generally a protocol data unit, a PDU, but I think a packet is more common nowadays. Or I'll use a packet more commonly. And we've encapsulated that data inside a PDU or packet by including headers. The headers are the extra information. For example, the source and destination addresses. In our simple example, application created data, send it to the transport protocol. The transport protocol adds 2 header fields, from address to address. Sends that packet to the network access layer. That adds another 2 header fields, from A to B. What fields does a protocol add? It depends upon a specific protocol. Different protocols do different things. But in general, a very common case is that we have data from one protocol sent to our next layer. That next layer adds some headers and then sends all of that to the next layer, which may add some headers, sends it to the next layer, and so on. What is sent across the link that is out onto the cable is the entire set of information there, the data plus all the headers. Segmentation we'll cover later. Sometimes we need to break those packets up, but that's a little bit more complex. We encapsulate the one packet from one layer into a packet from the next lower layer. And when we get to the receiver, we take it out. We take the large packet, remove the inner part, send it to the next layer. That removes the outer headers, takes the data, sends to the next layer. So what is sent by the application, this data block, is received by the corresponding application. The headers are there to support the protocol. I may be going through this quite quick, and it may be some very general concepts because we will spend the entire semester going through one protocol architecture. That is, we're going to spend all our lectures talking about the protocols at different layers, and you'll see more of this in more detail when we go through individual layers. And the one protocol architecture we're going to talk about this semester is we're going to call the TCP/IP protocol architecture. So our previous one, our 3-layer architecture, was just an example to show that we have layers and packets and so on. Probably in the 1960s, which is what, 40, almost 50 years ago, in the US, funded by the Defense Department, they were doing some research about connecting computers together. Okay, so mainly universities or large companies, large research organizations had some large computers, not laptops, but large time-shared computers. And they want to connect them together so that the universities can share access to those computers and exchange information. So the Department of Defense, or what became the Department of Defense, had a research unit, ARPA, and they connected some computers together in different US universities, and it became ARPANET, a network created by the organization ARPA. And the way that those computers communicated, and this is 40 or 50 years ago, was using several protocols. 2 of the key ones were called, or perhaps the most important was called IP. IP is short for Internet Protocol. And the other one was called TCP, Transmission Control Protocol. But there are others. But the 2 key ones to allow these university computers to communicate were TCP and IP. And that network of connecting several universities grew to connecting more universities across the US. In other parts of the world, they were building their own networks in different countries and regions, in Europe and so on. And over time, they started to connect those networks together. And so long as all of the devices were using the Internet Protocol, IP, they could connect and communicate between all the computers across the globe eventually. So that became what we have of the Internet today. It grew from this research network in the US using the protocols TCP, IP and others, and it's what we know as the Internet today. It's much more complex today, but that's where it came from. Because the main protocols are TCP and IP, it's often referred to as the TCP/IP or TCP/IP protocol architecture, protocol suite. So you'll often see TCP/IP, which refers to really a collection of protocols, not just 2, just as a name. That is the protocol architecture that we're going to focus on, and it's the main one in use today. It was started from the US Defense Research and universities, but nowadays there's other organizations that manage the protocols that are used, that is, design them and develop and enhance them. The Internet Architecture Board, and within that the Internet Engineering Task Force, the IETF, is an organisation that creates new protocols. These were created 40, 50 years ago. They've been improved over time, and new ones have been added to support different tasks. There's no official protocol architecture for the Internet. There's no one document that says that there are 6 layers or 5 layers. But what we're going to use, and what's maybe the most general accepted protocol architecture, breaks our architecture into 5 layers. And that's what we're going to use in this course. Sometimes they have different names. Sometimes you'll see 6 layers or even 4 layers, but we will use the 5-layer protocol architecture. It looks like this. There are 5 layers. From the bottom up, the physical layer, data link layer, network layer, transport layer, and application layer. That's our TCP/IP protocol architecture. In some textbooks you may see different names, or even you may see 4 layers like application, transport, network, these two combined as, say, the hardware layer. Or you may see this as not the network layer but the internet layer. So it differs in different sources. But the same concepts are applied, and this is perhaps one of the more common ones. That's what we're going to use through this course, where we're going to look at what are the protocols used at each layer to achieve different tasks for data communications. Starting from the physical layer, at the end of the semester we'll finish on the application layer. At the same time, roughly as the US were developing the ARPANET and expanding that, another organisation, ISO, was creating a different architecture. You would have heard of ISO. They are an international standards organisation. You may have heard of ISO quality assurance. They create many different standards, some related to communications. They developed what's called OSI, Open Systems Interconnection, around the 1970s. They developed a 7-layer architecture. There were not 5 like you see in the next slide, but 7 layers. Similar, but 2 extra. And they had their own products, or people implemented products that used this 7-layer architecture. It was different from the internet architecture. If I had my computer that supported the OSI architecture and you had yours that supported the internet architecture, they may not necessarily be able to talk to each other. They're using a different approach. We're not going to cover the 7-layer OSI reference model. The TCP/IP one, TCP/IP architecture one, that is, it became the most dominant throughout the world for different reasons. Some business, some technical, some maybe political. But TCP/IP is the primary architecture used today. There may be some old, very old networks that use the OSI 7-layer architecture, but not so common. Although many of the principles and terminology used from this are still used today. So you'll still see in textbooks, you'll still see in many online materials reference to this 7-layer OSI model. We're going to focus on the 5-layer model. Some examples of protocols or technologies used at those layers, some of them you'll recognise. At the bottom, the different media they're used for transmission. Okay, twisted pair. These cables, your LAN cables, it's not so easy to see. You can pass them around. There's several. You look at the endpoints and see how many wires there are. I've passed them around. That's just the typical LAN cable that you have, that you plug into your laptop or the back of your PC into one of the LAN cards. These are old LAN cards, maybe 15 years old. They won't, nothing exciting to see except where you plug the cable into it. Note the, while we're at it, one more device. This is just a switch where we connect our computers to. This has 8 ports, our computer normally has 1 port. Those LAN cables, you'll see from the endpoints there are how many different cables inside? You'll see 8 different coloured cables. Okay, some green, red, orange, and white. Those thin wires inside. In fact, inside each of them we have copper. And twisted pair comes from the name that what we do inside there is we take a pair, that is 2 copper wires, and twist them around each other for reasons to make communications or the signal handle interference. But twisted pair refers to those wires. Same used in your telephone, your home telephone cabling. Uses copper wires twisted around each other. Other technologies for transmission, optical fibre, wireless, and so on. They are considered part of the physical layer. That is, they are technologies for getting bits as signals across some link. What we send across those copper wires is an electrical signal. That signal represents a sequence of bits. And that's the primary role of the physical layer. Take bits from the higher layer, so zeros and ones, and transmit them across some media, some cable or wirelessly, transmit them as some signal. That's the simplest definition of the physical layer. Bits as input, transmit signals. There are many different types of signals we can send across different media. These are some example ones. And there's many different ways of how do we encode those bits as a signal. That's what the physical layer deals with. It doesn't care what those bits are. It doesn't care whether the bits are a web page, an email, or a large file. It just treats them as a sequence of zeros and ones, converts into some signal to send. The data link layer is about making sure that those bits which are sent across a link are done so in a reliable manner and to the right destination. So when I send wirelessly from my laptop to the access point on the wall, it's considered as a single link. The physical layer of my laptop is responsible for taking bits and transmitting some signal, some radio signal out from my laptop. And it would be received and processed by the physical layer at the access point. But when we transmit signals, life is not always fair in that we may have errors. I transmit a signal representing a sequence of bits, and what is received is not matching what was sent. The data link layer tries to deal with that and tries to, for example, fix those errors. So the physical layer is about getting bits as signals across a link. The data link layer is making sure that that data, those bits, are sent reliably across a link. Importantly, both data link layer and physical layer are dealing with a single link normally. Okay? From one device to another. Imagine a cable connecting this computer to another computer. Physical layer is how to get the information across one link, and data link layer is about how to get that information across one link in a reliable manner. Some examples of technologies relating to both of these layers really. Ethernet, your wired LAN, wireless LAN or Wi-Fi, and there are others. Data link layer, physical layer deal with a single link. Okay? But we know if I want to connect from my laptop to a server in the US, I don't have a single cable connecting directly. What I do is I send to the access point. The access point sends via the cable to some device downstairs. That sends to another device, for example, a switch or a router. There's a switch being passed around. And then eventually, through multiple links, reach a server in the US. Physical layer and data link layer deal with individual links. The network layer deals with getting that data across multiple links, across a network. So how do we get data from my laptop to a server in the US? It needs to traverse multiple links. The network layer implements protocols to make sure that we can get that data across all of those links. The primary protocol is called IP, or the Internet Protocol. And hence we have the Internet, using the Internet Protocol. Skipping transport, going up to the top, and we've mentioned this in our example 3-layer architecture, we have at the top application layer. Many protocols are included there that support specific applications. There's a protocol for supporting web browsing, HTTP. There's a protocol for supporting file downloads, FTP. Another one for email, SMTP. For connecting to other computers, you did it to get your password for the quiz, SSH. And hundreds of others here. I've just listed 4 examples. These are all application layer protocols. They're designed just to support an individual application at the application layer. Of course, some of these applications need to do the same thing, send the data reliably across a network. Hence, we have a transport layer which deals with reliable delivery of data across the network. Specifically TCP, the Transmission Control Protocol. That has the responsibility of making sure that when my laptop sends an email to a web server in the US, when it transmits that email across the globe, halfway across the world, that across that network, if there are any errors along the way, that the email that I sent and the email that is received are identical. If something goes wrong, the transport protocol, specifically TCP, will make sure that if there was an error, that error is fixed, so that the receiver receives an identical copy of what was sent. It's implemented in its own layer because many applications use it. Rather than implementing that functionality in individual application protocols, we separate it into its own layer, a node protocol. There are other transport protocols which we may mention later. You need to remember those 5 layers, the names, the ordering of them, and over time you'll need to know what they do. Okay? That is, what tasks do they perform in data communications? Physical layer, sending bits as signals. Data link layer, sending data reliably across a link, an individual link. Network layer, sending data across a set of links, across a network. Transport layer, reliably sending data across a network. Application layer, specific to individual applications. It depends upon the application. That's a very broad description of those layers. By the end of the course, you'll be experts on all of them because we'll go through them and specific examples of each. Instead of moving on now, let's go back to one thing we missed last week. I said at the end of last week's lecture, there's a map of the internet in Thailand. So we'll stop this topic now and let's look at that map. You all looked at it during the week, the internet map? Hands up if you looked at the internet map. Okay. You should look at it in your own time because it's much easier than seeing on the screen. Where is it? In the last 5 minutes, let's have a look at it. It was the last slide of last week's lecture. It's not printed on your slides because it doesn't come out very well. It's a map of the internet in Thailand. And in fact, there are 2 different pictures, and you can get them from a website linked in the lecture notes and on the website, course website. There is a picture of the internet inside Thailand, the domestic map, And then there's a picture of the connections from Thailand to other parts of the world, the international map. We'll zoom in a moment, but because it's not readable here. But let's just look at the structure of what we see here. It's an internet map, May 2012. These pinkish purple ellipse is representing internet exchanges inside Thailand. Let's describe that. Here's the CAT Internet Exchange. CAT is a telecommunications company. They provide connectivity within the country to many different internet service providers. Around the edge, these blue ones are networks of individual ISPs. You as a customer, you go to an ISP, whether it's True, TOT, TT&T, many different companies, the very small ones, Jasmine and so on. You go as a customer and say, I want to pay 600 baht a month to get internet access. And they connect maybe from your phone into their network or from some other technology. These blue ones represent individual ISPs inside Thailand. You as a customer have a connection into one of these blue ISPs. And then these blue ISPs all connect to one or more internet exchanges. There are several here. CAT has two, in fact, ADSE, Jasmine or Jazztel, True Internet Exchange, TOT, and other companies. So these are the large telecom companies. They provide connectivity to all the smaller ISPs, internet service providers. The lines are the connections. May not just be a single link, but show, when we zoom in, the speed or the capacity of the connections between one ISP and an internet exchange. Let's zoom in to see. Let's see what we see at the top. Okay, you may be able to see a bit more now. Okay, we have these blue ISPs around the edge. These are the, say, the consumer-based ISPs in most cases, something that you and I can go and pay a company to access via. Here we have True Internet, Triple T, TOT, and many others. As a subscriber of TOT, I connect from my home into their network, represented by this blue one here. And then they have links into the different internet exchanges. If you follow it, it's not easy. TOT, the ISP, has a link into the CAT exchange, and the capacity of that link is 21.99 gigabits per second. So that individual link has some speed at which it can send data. But they don't just have one link. They have connections to other exchanges for redundancy and for different commercial or different customers. So you have to follow individually. You may see this blue line here goes to, in fact, this blue one here from TOT, the ISP goes to the TOT Internet Exchange at 40 gigabits per second. So they connect from their ISP network into their Internet Exchange network. And there are others as well. So you can see the different speeds, 102 gigabits per second, down to 90 megabits per second. These they're in bits per second, not bytes per second. Yep.
Explain the purpose of the pink bubbles.
So what are the purpose of these internet exchanges? We'll see shortly. Well, first, domestic internet. What you as a customer do, you subscribe to one of the blue ones. And if you want to communicate with someone else in Thailand on a different ISP, rather than this ISP having a connection to this ISP and to every other ISP, they in fact just connect into an internet exchange. So if I'm on TOT and you are on PACnet, you subscribe to a different company, my data, if I send to you, goes to my local ISP. Possibly it follows this link into the CAT Internet Exchange, and then follows this link at 7 gigabits per second to the PACnet ISP, and then goes to your home. Okay? So the Internet Exchanges connect the ISPs together, rather than every ISP having to connect directly to every other ISP. If every blue one connected to every other blue one, there'd be thousands, tens of thousands of links there. Here, there are just tens, hundreds of links, centralized through Internet Exchanges. And the others. It's worth looking at in your own time, because you can zoom in on the parts that you recognise, find your own ISP possibly. That's the domestic network. But then what happens when we want to communicate with someone outside of Thailand? Well, in other countries they have their own domestic networks, but we connect to ISPs in different countries. This is the international network. These are international internet gateways. They're within Thailand. They have connections from either the domestic internet exchanges and the domestic ISPs to ISPs in other countries. All these grey boxes, we'll zoom in, all the grey boxes represent internet service providers overseas. And again, the links are between the international internet gateways, CAT, Jasmine, True, TOT and others, to international ISPs. Just in the last couple of minutes. Maybe we zoomed too far. Just along the side here, some of those international ISPs are in US, in Korea, in Indonesia and so on. They're just different companies in other countries. And they have links into the international gateways. So now when I connect I want to send my data to someone in Indonesia, for example, it may go from my ISP to a national exchange to an international gateway. In fact, the national exchange and international gateway may be together, and then to Indonesia. I don't know if I can follow the link, but one of these links that come into the Indosat, for example. In fact, Indonesia Satellite Network. These are ISPs overseas. And the speeds of the links between them. And then once it gets into the US or Indonesia, then it goes through their domestic network, however that's structured. Note that also some companies like Google and Microsoft and IMEME, they are not really ISPs, they provide content. You cannot subscribe to Google as an internet service provider customer, but you access their content. So in fact, in the last few years, they've been creating direct links into Thailand so that when you visit the Google website, instead of connecting via other ISPs to the US and so on, you connect direct, or from the international gateway inside Thailand, direct into Google's network, either in Singapore or in Malaysia. And at speeds, you'll have to follow the lines to see the speeds there. And you'll see Microsoft, Yahoo and others there as well. That saves them money. They don't have to pay other ISPs for their traffic, and it normally provides faster access for you and I, in that we access Google directly. Enough for now. We're out of time. Have a look at these in your own time. You'll see them on the website. And just look at some of the things, some of the companies you can recognise, and get an idea of the structure of the internet in Thailand. Tomorrow we'll keep going on protocol architectures and look into some more detail about protocols and architectures. Enough for today.